To be here. Thanks for joining this seminar, and thanks for inviting me for this talk. So in the following, I'm going to present research results entitled Is Whether Chaotic, Coexisting Chaotic and Non-Chaotic Attractors and the Time-Varying Multistability within a Generalized Relevance Model. My name is Bo-Wen Shen from San Diego State University. I'd like to thank the following co-authors and the colleagues for their help and valuable discussions. I'd like to present this talk in memories of my father who passed away last month. Right now, I'm still in Taiwan. I hope the network connections will remain good during this presentation. So here's the outline. I will first present you Saturday estimations to address our goal and approaches. There are three parts. In part one, we're going to review major features of those models in order to provide a revised view on the dual nature of chaos and order. First, we are going to review major solutions of Lorenz 1963 model and generalized Lorenz models, including coexisting chaotic and non-chaotic attractors, monostability and multistability. Then we are going to discuss Lorenz 1969 model that produce various types of solutions and possess ear conditioning. In part two, we are going to revisit a conceptual multiscale models based on time-varying multistability from generalized Lorenz model. In part three, we are going to present additional features of Lorenz models that can help us analyze the data from real-world model simulations. At the end, I will give a summaries. In the appendix, I have additional slides that discuss the impact of nonlinearity using idealized ODEs, and also provide comments on the conceptual model of trend processes within the L69 models. It is known that studies by Lorenz at MIT in 1963 and 72 laid the foundation for chaos theories that is viewed as the third scientific achievement in 20 centuries after relativity and quantum mechanics. In methodology, Lorenz study yielded the statements of whether it's chaotic and suggested a limit of probability for 2 weeks. However, the validity of the above findings is being challenged by 30-day global model simulations, including our 30-day simulations of multiple afterglacial wave, published in 2010, 30-day simulations of MJO, published in 2011. Since then, we start thinking whether and how high-resolution model can have a scale at extended range time scale. Gradually, we realized we need to address the following questions, including what type of sensitivity do those models possess? Is whether chaotic? Is whether a 2D or 3D turbulent flows? To achieve the above, during the past 10 years, we have done the following activities in the categories of modeling: observation, analysis, synthesizing, and theorizing, which is referred to as MOST. Today, we are going to provide a review on some of these. In part one, we are going to review major features of Lorenz models in order to provide a revised view that focuses on the dual nature of chaos and order. The following articles entitled Is Whether Chaotic was just published by Benz earlier this year. And later, we're going to provide an insightful analysis of L69 models showing various types of solutions and another type of sensitivity. Before I'm going to discuss those models, I'd like to provide the following quotes as my personal view on the role of idealized models. This quote states, this model will be a simplification and an idealization, and consequently a falsification. It is to be hoped that the features are those of greatest importance in the present state of knowledge. The above quote is from Tunis' paper published in 1952. Turing is well recognized as the father of theoretical computer science and artificial intelligence. Based on the above, we suggest that an idealized model may be developed to reveal major features of a target systems. However, such model should be regularly revised to include new features. With this type of understanding, we are going to review Lorenz 1963 models, which is based on a system of a PDE for the so-called Rayleigh-based convections. The system of a PDE describes the time evolutions of a verticity and the temperature. Lorenz applied 3 Fourier modes to convert the system of a PDE into a system of ODE as shown here for 3 state variables x, y, z. The model also contains 3 time-independent parameters, including R, sigma, and B. R is called Rayleigh number or heating parameters, which is a measure of temperature differences between top and bottom layers. By comparison, the generalized Lorenz model is shown on the right-hand side. Based on what you can see, it appears very close to L63 models. In the third equations, we add the XY1 term based on the extension of a nonlinear feedback group. This type of a concept was first published in 2014. This additional term introduced an additional pair of smaller scale modes. As a result, the original XYZ are referred to as primary scale modes. This type of extension can be repeated through XYJ plus 1. J is integer starting from 1. And each extension is going to bring additional pair of smaller scale modes. As a result, GLM allowed any up number modes. GLM was first published by a IJBC article in 2019 entitled Aggregated Feedback in a Generalized Lorenz Models. IJBC stands for International Journal of Bifurcation and Chaos. Currently, this paper is being listed as one of the most read articles by IJBC. On the same list, I have another paper with my students, and this paper was selected as one of the featured articles for 2018. To provide the physical relevance for real-world application, we additionally compare Lorenz model in the second column with Pedlosky model in the third column. The Pedlosky model is based on 2-layer quasi-geometric system for baroclinical wave. Although these two systems are from very different PDEs, the ODE can be mathematically identical if we choose parameter properly as shown here. Such a comparison reveals the idea of the following quote. Mathematics is the art of giving the same name to different things. This is from Poincaré. He is also known as one of the fathers for chaos theories. In Paris, France, there's an institute in his name. It was my honor to give a talk in 2019. We additionally compare non-dissipative model on the left-hand side with different physical systems on the right-hand side, including Duffing equation, nonlinear Schrodinger equation, KdV equations. Based on the equations in red, the left-hand side represents non-dissipative Lorenz model for Z components. The right-hand side represents the KdV equations in the traveling wave coordinates. If we choose C equal to 4R, two systems are identical. The solutions to the system is hyperbolic secant square function, which is also known as solitary wave solutions. Earlier study already showed that a Rho cloud like this may appear in the form of a solitary wave solution. One of the major features for L63 model is SDIC, sensitive dependence on initial condition, that has been applied to define butterfly effect or chaos. The following figure has been widely used to illustrate SDIC that compare control and pair runs. These two runs using the same model and the same model configuration. The only difference is their initial conditions. we add a tiny perversion epsilon into the initial conditions for pair 1. Epsilon is equal to e to the negative 10th. We then compare solutions as a function of time. Horizontal represents time, vertical represents solutions. Initially, we only see one curve in red, indicating two solutions are almost identical. This feature is called continuous dependence on initial condition, CDIC. Later, we do observe two different curves, one in red, the other one in blue. These differences are associated with tiny perversion in the initial condition. As a result, this feature is called sensitive dependence on initial conditions, SDIC. The solutions are called chaotic solutions. A combined CDIC and SDIC suggests finite probability. Simply speaking, probability is determined before the onset of SDIC. In 1993, Lorenz published a book entitled The Essence of Chaos. He used a scheme to illustrate SDIC. Say we have a slightly different starting point. We may have a very different path as a result, different destinations. As a result, SDIC indicates the sensitive dependence of a time-varying path on initial conditions. Although chaotic solutions has been a focus for several decades, Lorenz model also produced non-chaotic solutions, which are discussed here. We first define RC as the critical values of a heating parameter for the onset of chaos. RC can be determined analytically as 24.74 and the capital RC as 313. Based on the relative strength of heating, the model produced three types of solutions: at small r, medium R, and large R. In each of these cases, we are going to compare control and the pair runs. For the first case, with R less than RC, control and the pair run produce almost identical results. Solution approach a constant as time proceeds. These are steady-state solutions. When R is greater than RC, as discussed earlier, control and the pair run display SDIC. These are chaotic solutions. Very interesting, when R is sufficiently large, which is greater than capital RC, the system produces nonlinear oscillator solutions, which is also known as limit solutions. The corresponding solutions in two-dimensional phases is shown below. A comparison among these three cases suggests that chaotic solutions appear within a finite range of heating parameters. Here, we can provide additional analysis for the chaotic solutions. For example, during this time interval, we observe regular oscillation associated with a spiral source. During this time interval, we observe irregular oscillation associated with saddle points. We may use track prediction to illustrate these two scenarios, including Hurricane Ivan in 2004, Hurricane Sandy in 2012. This slide provides a detailed analysis, including incrementally and rapidly divergent
NTFS format.
Rapidly divergent trajectory. We can discuss this during the Q&A sections. Lorenz model produced both chaotic and non-chaotic solutions. In fact, earlier study already applied non-chaotic solutions on the right-hand side to understand the dynamics of different weather systems on the left-hand side, including blocking, QBO, low-frequency variability, vortex shading, rock clouds, and the aftercluster wave. And very interesting questions becomes whether chaotic and non-chaotic solutions exclusively appear. The answer is no, because within a generalized model, we can show that chaotic and non-chaotic solutions may coexist, which is referred to as attractor coexistence. Attractor coexistence is enabled by the so-called aggregated net feedback, which will be discussed later. As discussed earlier, GLM allowed any up number modes. Using this slide, we are going to introduce the concept of monostability and multistability. Given a model configuration, L63 model produce single type of solutions, which is called monostabilities. Within chaotic solutions, SDIC always appear. By comparison, GOM allowed attractor coexistence. Chaotic and non-chaotic solutions occupy different portions of a phase space. This feature is called multistability. As a result, SDIC may appear or may not appear, depending on whether tiny perturbation is associated with chaotic orbit or non-chaotic orbit. Previously, we used a scheme to illustrate SDIC. This photo can be used to illustrate monostability. For example, if the slopes are steep everywhere. By comparison, we may use kayaking to illustrate multistability. Here, we do observe strong currents and also relatively stagnant currents as indicated by white box. As a result, this photo reveals both instability and local stability, indicating multistability. Next, we are going to discuss L69 models, which is based on simpler PDE. Compare this one, this is simpler. And this PDE represents the conservations of verticity. Lorenz applied 21 modes to analyze these systems. As a result, the so-called L69 model is multiscale. The other features of linearity and the ear conditioning will be discussed below. Lorenz also proposed different models in 84 and 96. We are not going to discuss today because these two models are not PDE based. The top panel displays the title of L69 models with a focus on probability within a multi-scale systems. Bottom panels display the energy spectrum as function of horizontal scales. Major findings in this study including finite probability at a specific scale, probability dependency on scales, large growth rates over smaller probability at smaller scales. A finite interval of a reliable prediction cannot be lengthened by reducing the amplitude of initial errors. Later, we are going to provide comments on the last findings in rate. Based on the conservations of verticity, Lorenz applied modified quasi-normal closure and linearizations to obtain a linear system of a second-order ODE as shown here. Z is a column vector consisting of n state variables. Each state variable represents error energy at a specific scales. C is n by n matrix representing the coefficients for the state variables. Each element is determined by the mode interactions. Based on the analysis of equations in red box, the system is physically multiscale because of n state variables. However, it's mathematically linear. To analyze a linear systems, a typical way is to assume solutions in the following form. Then we can convert a system of ODE to a system of algebra equations representing an eigenvalue problems. Now, sigma square represents eigenvalues of the matrix C. The reason we have a sigma square instead of sigma is because the original system is a second-order ODEs. Based on the analysis of eigenvalues, we can show that the system produces various types of solutions with positive and negative eigenvalues. The system is air-conditioned. Easy capture numerical instabilities. Today, we are going to discuss the features in B and V. The so-called air conditioning is indicated by a large conditional number, which is defined here. Based on the second formula, we understand the conditional number is determined by the magnitude of a ratio between the largest and the smallest eigenvalues. And based on the analysis of a conditional number, we analyzed 6 matrices from these 2 studies by Rontuno and Duran. And these 6 matrices produce systems comparable to L69 models. Their conditional numbers are shown in the second and the third columns using Python and MATLAB. As you can tell, these conditional numbers are large, indicating these systems are ear conditioning with numerical sensitivity. Below, we are going to illustrate the numerical instability of L69 model based on a simpler ODE that produce an eigenvalues of 10 pi square, leading to a growth rate or decay rate of square root of 10 pi. The following initial conditions produce physically stable solutions as shown here. Its value is shown in the third column, which decreases with time, indicating stability. However, when Runge-Kaldor scheme is applied, the numerical solution is shown second column, which increases with time, indicating instability. The reason we have instability is because numerical error may introduce non-zero coefficients for unstable modes. Okay. As a result, error amplifies as time proceeds. Eventually, the unstable mode dominates. Okay. Based on analysis of those 1969 models, it is ear condition and easy capture numerical instability. As a result, major findings are shown in red should be interpreted as the features of a model instead of the true natures of a weight. It may represent partial natures of a weight. Okay. So therefore, an important message from this is a better probability may be obtained using different models or methods. What we discussed for part 1 can be summarized here. Here we present 2 types of sensitivity. The first one with SDIC has been applied to define chaos. The second one with ear conditioning can be found in Lorenz 1969 models based on various types of solutions within L63, 69 models, and attractor coexisting within GOM, which suggests a revised view on the dual nature of the chaos and order. With the feature of those models, we now discuss 2 kinds of probabilities. Intrinsic probability depends on flow itself. Predictable probability depends on model or initial conditions. L63 model is very effective reviewing chaotic natures of a weather, suggesting finite probability. GOM emphasizes the coexistence of chaotic and non-chaotic solutions, suggesting both limited and unlimited probabilities. In the beginning, we mentioned, okay, there's a possibility for us to obtain 30-day predictabilities. Based on the analysis of L69 models, we show that this model is very effective at reviewing multiscale interactions. However, the major findings with finite probability should be interpreted as the features of the models. Below, we are going to revisit a conceptual model for multiscale processes of hurricanes based on additional features of high-dimensional models, including time-varying multistability and hierarchical scale interactions. Previously, we illustrated the model produced 3 types of solutions based on time-independent parameters. Now, if we consider periodic forces as shown here, horizontal represent time, vertical represent the strength of heating. Okay. During this, using these periodic forces, we may expect steady state solution appear during this time interval, chaotic solutions during this time interval, and at a large R, we expect limit cycle solutions. Since the heating function is periodic with time, we may expect these solutions appear alternatively leading to the so-called time-varying multistabilities. More detail can be found in these figures that has been published by Benz. To simplify the discussion, I'm going to skip the detail. Instead, here I want to emphasize that although at earlier time solution may appear chaotic, once the heating is getting stronger and stronger, these solutions may still become nonlinear oscillatory, which is regular solutions. Since the GLM allowed multistability as a result, when a periodic forcing is applied, we may expect time-varying multistability. As a result, the GLM produces time-varying multistabilities, which is modulated by large-scale time-varying forcings. More importantly, the multistability is enabled by the aggregated neck feedback, which may produce local stability. And we are going to discuss next. The so-called aggregated neck feedback has been discussed using mathematical equation in the paper. Here we simply present the result. The first color indicates number of modes. The second color indicates the values of RC. RC represents the critical value of a heating parameter for the onset of a chaos. RC are determined based on the analysis of their polynomial exponents. A comparison among 3D, 5D, 7D, and 9D suggests that higher dimensional models require larger R for the onset of chaos, and this indicates aggregated net feedback. Smaller scale modes may introduce negative feedback to the systems. And more important, all kinds of negative feedback can be aggregated to provide stronger dissipation. As a result, higher dimensional models require larger heating parameter for the onset of chaos. More importantly, the so-called aggregated net feedback may lead some of unstable critical points to become stable, leading to coexisting of chaotic, stable and unstable critical points, yielding attractor coexistence. Another feature is hierarchical scale dependency, which can be illustrated using 7-dimensional model. And at earlier time, we illustrate these scale interactions using global mesoscale models. Based on what we discussed, we can revisit a conceptual model proposed in 2010 in these triple scale systems. If we would like to focus on simulations of a tropical cyclone at a medium scale, we would like to understand the modulations of a large scale system through the downscaling processes. We also would like to understand the feedback of a smaller scale systems through the upscaling processes. And during the past several years, we already developed tools, including PMD and SAT. Today, we're going to discuss PMD. At the earlier time when I present this, I often provide the following analogies. For example, if we focus on performance of a department, we would like to receive a strong support from school or college. We also would like to receive a strong support from individual faculty. And during the past several years, we have a published paper focused on the relationship between tropical cyclone formation and the equatorial tropic wave, large scale wave, including equatorial Rossby wave, mixed Rossby gravity wave, arbitrary easterly wave, and the multiscale resistance. And the following slides are prepared for the first two scenarios. I'm going to skip for now. Instead, I'm going to discuss the third case. I focus on formations of Hurricane Helene and arbitrary easterly wave. In our earlier study, that presents 30-day simulations from day 22 to day 30, our model simulated storm. We then plot this location as function of time in rate. And during this same period, there was a real Hurricane Helene between September 12 and 24. We then plot a space track for comparison. The corresponding intensity are shown on the right-hand side. Horizontal and the vertical represent time and the minimal severe pressure. As you can tell, during this period, the model was able to capture the rapid intensification, but did not produce over-intensified storms. We were lucky to publish the result quite smoothly 10 years ago. Related results also appeared in a review articles in 2019. This slide provides additional analysis for the same case. Panel A displays the structures of arbitrary state jet. The left-hand side represents from the GSF analysis. Right-hand side is from model. Panel B displays the simulations of a model and compare with normal observations. Panel C displays the simulations of multiple arbitrary wave that was compared with model simulations that was compared with analysis in the paper. Panel D displays the track and intensity predictions we just discussed earlier. Below, we are going to apply linear cycle solution to understand the property of arbitrary wave. A linear cycle solution is defined as an isolated closed orbit. Here, we illustrate 200 orbits in different color during the time interval between tau equal to 1 and 10. We also plot these 200 orbits in black during the last one time unit between tau equal to 9 to 10. And through this representation, you can see how 200 orbits eventually converge into a single orbit, indicating isolated natures. As a result, you can tell the linear cycle solution is not sensitive to initial condition because 200 orbits converge into a single orbit. On the other hand, if we plot two of them as function of time, which is shown on the bottom left, horizontal represent time, vertical represent the solutions. After initial pair of time, you can see two solutions already produce comparable amplitude and frequency, indicating these two solutions already converge into a single orbit. However, these two solutions still display differences in their phases. As a result of the dependence of phases on initial conditions, we obtain oscillator errors if one of them is true solutions. A message from this analysis is that when we analyze real-world data, we obtain oscillator errors that may be an indicator for oscillator solutions. We then apply that kind of a concept to analyze the 30-day simulations for Hurricane Helene. Horizontal represent time, vertical represent correlation coefficients of 850 millibar temperature against analysis. And during this 30-day period from August 22nd to September 21st, the correlation coefficients are above 0.6, indicating a good predictions. However, this result display oscillatory behavior, indicating oscillatory solutions. In the paper, we additionally compare these two scenarios. Linear cycle solution appear at a large heating parameter, right? On the other hand, arbitrary wave appear during the summertime when strong solar radiation occur over African continents. As a result, we suggest that realistic estimations of Hurricane Helene from day 22 to day 30 become possible when we can obtain realistic simulations of recurrency of multiple arbitrary waves and the downscaling process of the first arbitrary wave. For example, after formations of 4 arbitrary waves, a model may produce a probability of 20 days because an average period of arbitrary wave is 5 days. If the model is able to simulate the downscaling process of the first arbitrary wave, it's going to add additional 3 to 5 days probability. As a result, we may have 25 days of probability. Below, we are going to illustrate scale interactions based on so-called PMD, parallel ensemble empirical mode decompositions. You may simply apply the Fourier transform to understand this. After data decomposition use PMD, we obtain two modes. Here, we only analyze two modes. One represents arithmetic wave. The other one represents basic state. Horizontal represents time. As you can tell, two modes display an opposite tendency, indicating energy transfer from basic state to arithmetic wave. And during this period, we also plot the minimal silver pressure for Hurricane Helene. As you can tell, all of the three curves produce consistent results. We also apply this approach in a 10-year data analysis. Statistics are shown on the top right, and related result has been published in 2016. Below, we are going to discuss the digital features that can help us analyze the model data. We're going to focus on these two: saturation dependency on various types of solutions, dependency of computation chaos and time state. From these slides, I'd like to provide one sentence summaries, which is written as follows. Given the same number of Fourier modes, we can derive different generalized models with different properties. More detail we can discuss during the Q&A sessions. In this slide, we're trying to identify three physical processes based on those models, including heating, nonlinearity, and dissipation. We then introduce additional parameters, transform the L63 model into an alternative form in order to illustrate individual or correct impact of all of the terms. As a result, we can first illustrate the correct impact of heating and the nonlinearities. Such a system produces oscillatory solutions without chaotic solutions. However, when dissipative terms are added, the system produces three types of solutions. As a result, we can classify these three types of solutions based on the strength of dissipation as well. These three types of solutions appear at large dissipation, medium dissipation, and small dissipations. For steady state solution approach constant as time proceeds, right? This already indicated saturations. For chaotic solution, we know that the root mean square error becomes saturated when a sufficiently large ensemble member is applied. By comparison, a large heating parameter or small dissipation, the system produces nonlinear oscillator solutions, producing oscillatory differences. As a result, oscillatory root mean square errors indicate oscillator solutions. That has been documented by Lu et al. In 2009 using NCAR models. And the following two slides provide analysis of a saturation between 1D and 2D systems. I have additional 7 slides regarding this we can discuss during the Q&A sections as well. Instead, I want to emphasize, in order to detect saturation, it is important to identify instability, nonlinearity, and also dissipations. For the first one, it is important to understand the features of a forcing, for example, the time scale or durations of instabilities. Below, we are going to discuss the role of dissipative and smoothing terms. Previously already showed that chaotic solutions appear within dissipative Rose models, with dissipation that including Nabla square theta. By comparison, turbulence appear within dissipative systems with Nabla square U. As a result, the inclusion of a dissipative term is crucial for appearance of chaos and turbulence. Below, we are going to say the relationship between smoothing term and the dissipative terms. After that, we suggest that smoothing term may introduce temporal complexity of solutions. Based on diffusion equation on the top, we can derive equation 23. The right-hand side represents an average operators. So this slide say the relationship between Navier square operator and the smoothing operators. And this study provides examples showing how damping term may introduce complexity of solutions. The following quote is from this paper. As strength of the divergence damping increases, the model produces a continuous increase of a global number of DCs and hurricanes with little change in storm mean intensity. Okay. Below, we are going to discuss computational chaos. The computational instability is defined as unbounded amplifications, and that is very different from chaos. Computational chaos means chaotic behavior associated with large time step. And based on what we discussed earlier, we suggest that numerical dissipation may turn nonlinear oscillator solution to irregularly chaotic solutions, yielding error saturation. Here are provided examples for computational chaos. We begin with logistic equations with differential equations. This system produces analytic solutions without chaotic behavior. Solution approach a constant. When we apply finite difference, we may convert this equation into a difference equations, which is called logistic map. As we know that a logistic map produces bifurcation and chaos at a large rho. The rho is function of delta t. As a result, large rho means large delta t. Similarly, bifurcation can be also found in the following equations for terminal velocity. And this has been documented in my first chaos paper in 1995. I'm going to skip this for now, this as well. Okay. I would like to emphasize them regarding the memories of initial conditions. Based on this simple ODE with periodic forcings, the system produces transient solutions that shows dependence on initial conditions, C, right? And this system also produces steady state solutions, which is independent of initial conditions. As a result, when we add a new term or new component, no matter that is length, oceans, we may ask, okay, how this new term or new component is going to change the transient solutions or steady state solutions. And here is there will be comparison between isolated limit cycle solutions with linear oscillator solutions that display dependence on initial conditions. The left-hand side does not depend on initial conditions. Okay, and then now I'm going to give a summary. In this talk, I discussed two types of sensitivities. One with SDIC has been applied to define chaos. The other one is associated with air conditioning. The L63 model is a limited scale, nonlinear, with monostability. It is very effective review of SDIC, suggesting finite probability. L69 model is closure-based, multi-scale, linear model with air conditioning. It's easy capture numerical instability. As a result, the major findings of finite probability should be interpreted as the features of models. GLM focus on multistability, suggesting both limited and unlimited probabilities. As a result of saturation dependency on various types of solutions, Oscillator solution may be indicated by oscillator root mean square errors. On the other hand, oscillatory solutions may appear as computational chaos due to insufficient model resolutions. The so-called time-varying multistability is enabled by aggregated negative feedback and large-scale time-varying forcing, and it supports the conceptual model of multiscale interactions for TC. Based on the above, we suggest a revised view on the dual nature of chaos and order. Such a view is neither too optimistic nor pessimistic. The view may unify our understandings of a theoretical probability and promising 30-day estimations that beyond 2 weeks. In the future, we would like to apply the following method to detect nonlinear oscillatory signals and also improve simulations by avoiding computational chaos. Here's a list of selected references. Here's takeaway messages. 2 types of sensitivities, dual natures of chaos and order. This concludes my talk. Thanks for your attention. I'm taking questions and comments from now. Thank you.
Thank you, Bo-Wen. Any questions? Or any comments?